Hello everyone, my name is Hiago Rocha and I'm a PhD student at the Federal University of Rio Grande do Sul. In this video, we will present the paper, a routing-based genetic algorithm for task mapping on MPSoC. In this presentation, we will give an introduction and a motivation concerning the tackled problem. Then, we will describe the proposal starting with the routing model and then showing how we embedded it in the proposed RMGA. After, we will present the methodology and the results. Finally, we will conclude this presentation with final considerations and some future works perspective. In the past years, multiprocessing system on chip, or MPSoC, has become a widely adopted solution to meet embedded applications' high performance requirements. With dozens to hundreds of processing elements, MPSoCs can exploit the application threads or task-level parallelism (TLP), providing benefits in diverse domains such as communications, signal processing, and multimedia. To efficiently communicate the different MPSoC components, it is necessary to design a communication model that can afford parallel communication. Nowadays, a common approach is using the Network on Chip architecture, or NoC architecture. Therefore, in a NoC-based MPSoC, TLP exploitation is possible due to parallel applications execution on processors and communication parallelism provided by the NoC architectural structure. The ideal scenarios for a NoC-based MPSoC is when all tasks have satisfactory execution and the communication among them has the minimum possible delay. In these scenarios, an application presents a real improvement in terms of execution time, power dissipation, energy consumption, and communication latency. However, to achieve this real improvement, some challenges need to be addressed, such as core types and quantity, memory hierarchy, communication, task mapping, and routing. In particular, the mapping problem is NP-hard. Therefore, existing exact algorithms can solve small-size problems, but the processing time becomes infeasible as the problem size increases. This figure gives an example of a task-to-core mapping considering a syntactical application represented as a directed and weighted graph. On the other hand, once the mapping solution is known, the routing problem can be efficiently solved. However, when the mapping solution is not known, the deterministic routing strategies are commonly used, such as XY and odd-even. This figure shows an example of some applications task communication when using the XY routing algorithm. It's worth to note that the mapping and routing problems are highly dependent, since finding a routing solution requires finding a mapped solution. Based on that observation, in this paper we consider the mapping and routing problems from a new perspective, in which the task mapping solutions are found concerning the routing solutions costs. The main contribution of this work are the proposal of the routing model genetic algorithm that uses exact routing solutions to guide the optimization process, and the model of the routing problem that can be embedded in other mathematics algorithms to find optimizing mapping and routing solutions. Regarding the related work from the literature, most of them use the flow distance product minimization, which forces the application tasks to be placed closer, neglecting eventual congestion in the NoC channels as the communication traffic increases. The main difference of our proposal is that instead of using the flow distance minimization or executing the entire application in the optimization process, which may require much time, our approach takes advantage of the NoC features captured by the integer linear programming model and uses this model to find optimized task mapping solutions. Now, represent the proposed routing model. The model has some input data. A binary matrix X, which represents a mapping solution. A flow matrix F, indicating the amount of information transmitted among the communicating tasks. A binary matrix L, representing the target NOC topology. The data cap, which specifies the maximal bandwidth of all NOC channels. N is the total number of system cores. T is the total number of application tasks. And V of I, representing all the cores that are directly connected to a specific core I. Finally, the decision variable Y is a binary matrix that indicates if a link connecting cores I and J are used to communicate in tasks S and C. Moving on to the equations. The model objective function aims to minimize communication latency. For that, it considers the information flow F and the decision variable Y. The objective function minimizes the number of links used for each communication multiplied by the amount of information transferred in those communications. The constraint 2 ensures the distributions of information in the NOC links by restricting the amount of information that can be transferred in each of them. The constant 3 defines the objective function will consider only valid links. The constraint 4 ensures the conservation of information in the network. It defines that the amount of information provided as the output of some communication must be the same as their total amount of information. The constraint 5 ensures the conservation of information in the NOC links. It defines that the amount of information provided as output of a link must be the same as the amount of information provided as input. Now, we will describe the implementation details of our proposed genetic algorithm. A crucial part of our proposal lies on the objective function evaluation. The algorithm performs it by running an optimization tool. The optimization tool takes as input a mathematical model and returns the exact solution's objective function for the given model. In this work, we use the GROB optimization tool. We represent the chromosome structured as a vector where the indexes are the tasks and the vector elements are the cores. These are the main steps of our proposed genetic algorithm. The initial population is generated randomly according to a uniform distribution. As the selection operator, the algorithm uses a binary tournament where two solutions are randomly selected and evaluated considering their fitness function values. The algorithm uses the binary crossover operator. In this case, it combines the genetic code of two selected parents, generating the other two new solutions. The algorithm performs this procedure by replicating the parent genetic code through a complete sequential evaluation of their chromosomes, applying a probability of 50% to choosing a genetic code from one of them. The mutation operator randomly chooses two allocated tasks to perform a change. This procedure is applied to twins. Then, iteratively, the algorithm performs all these steps until the stop criterion to be satisfied. As the stop criterion, we choose a specific number of objective function evaluation defined by a parameter tuning tool. Moving on to the methodology of our experiments, we evaluated 6 applications that are widely used in the mapping problem literature. For comparison, we selected two genetic algorithms from the mapping problem literature. This work considers a classical genetic algorithm implementation in terms of genetic operators, selection, crossover, and mutation, and use a fitness evaluation based on the minimization of the flow distance product. We used the Knox-in simulator to perform our experiments, keeping some parameters set to the default values such as fleet, packet, and buffer size. In this work, we focus on evaluating the communication latency given by the global average delay and the maximum delay matrix. Since we intend to evaluate the algorithm's performance over high congested NOC traffic, we vary the packet injecting rate from 0.1 to 1.0. Also, we used the XY routing algorithm to compare all genetic algorithms. As the simulation stop criterion, we consider either the delivery of 10,000 fleets or the simulation achieved 100 million cycles. We vary the NOC dimensions from 4x4 to 10x10. In other words, the compared genetic algorithms are optimizing problems with sizes varying from 16 to 100. Finally, we performed 30 experiments for each combination of the evaluated aspects: applications, packet injected rate, and NOC dimensions. As the execution environment, we ran our experiments in a Intel processor, which is composed of 4 GB of main memory. Now we present the experimental results. These charts present the performance of all compared algorithms in the global average delay and maximum delay metrics per application. As it can be noticed, the RMGA presents the best result in almost applications. RMGA presents gains varying from 2 to 4% in the global average delay matrix over the Tucson's proposal, and from 8 to 25% in the same metric over the Gomes proposal. In the maximum delay metric, the results are similar. In this case, RMGA results varying from 2 to 5 over the Tucson's proposal and from 5 to 30 over the Gomes proposal. Now, we present a comparison among the algorithm delays as we increase the NOC dimension. In total, we evaluated 42 scenarios. The RMGA presents the best results in 31, which represents roughly 74% of all simulations done. Finally, this chart summarizes the results by showing the percentage of how many simulations each compared algorithm outperformed the other by the packet inject rate variation. For the global average delay metric, it's possible to observe that the RMGA presents the best results in more than 75% of all simulations considering all packet inject rate values. For the maximum delay metric, our proposal presents the best results in more than 70% of all simulations and more than 75% in the simulations with packet inject rate values higher than 0.3. In this work, we proposed the route model genetic algorithm. The proposed approach considers a routing model as a fitness function instead of a classic flow distance analytical evaluation to guide the search process. Overall, RMGA presents the lowest global average delay in more than 75% and lowest maximum delay in more than 70% of all simulations compared to the older GA from the literature. As a future work, the proposed routing model can guide the search process of older meta-risk from the literature. Besides, we intend to provide its adaptations for dynamic mapping. Thank you everyone for watching.